Alrighty. In this one, I want to talk about uncertainty. We're going to focus in on accuracy and precision and kind of get a good grasp of what these things are as we do that. Okay. This is we're gonna have to start off by thinking about two different kinds of numbers, and that sounds weird, but we have exact numbers and we have inexact numbers. Okay. Exact numbers um, are things that we say they have infinite precision. Okay, just meaning that um, they are super precise. They're very well known, and they're exactly what we say they are. So these are things that are in the same unit system. These have been defined to be exact. There's a handful of special ones. We'll see some of those. Infinite precision. Oh gosh, sorry. All right. These are things like when you're counting, if you say, okay, there's 12 pencils in my cup, then that's an exact number because you can literally count that there's 12 pencils there. Okay. And integers in an equation. So when we look at our temperature equations, all those integers, well, there weren't really integers in there. Like the 9/5 in there, those are integers, so those are exact. Okay, we're gonna hopefully make more sense of that as we go. Okay, inexact numbers are measured data. Okay, these are inexact because they depend on the measuring device. They depend on the reader of the instrument, and so when we get into lab and get our hands on some stuff, we're going to see how that works and what happens with that. Um, they also depend on the calibration of the instrumentation. Is it treated correctly? Is it well cared for? Is it high quality instrumentation? And we care about what the resolution is. And when we talk about resolution, um, I like this picture from from our book here that has uh, a ruler measuring the width of this USB stick. Um, this bottom one has a greater resolution because there's more detail between the markings. Okay, here there's not a lot of resolution because there's less detail. Okay, so the more resolution it is, the better your measurement can be. Okay. Let's talk about ways we can measure things. This is the same amount of this blue solid on two different digital balances. Okay. With a digital instrument, it's really nice because you get to uh, just read what the digits say, and the balance tells you exactly what the mass is. So here, this one says it is 10.5 grams. This one says it's 10.4977 grams. It's technically the same mass. It's the same thing. This one is more precise because it has more digits to it. So that's something else we want to think about. The more digits your number has, the more precise it's going to be, as long as they are significant digits, and we will get into that. Okay. This number is less precise because it only has 3 digits to it, where this has 6 digits to it. Okay. Uh, so we have digital balances like this, so it's gonna be really easy for us to be able to read mass with a lot of precision. Uh, Another way to measure things is analog instruments. This is probably what you think about when you think about measuring stuff. Um, Analog forces the user to interpret what the measurement means, okay? How to read this. So like these are rulers. Um, this is some sort of volume device. I'm gonna guess that's a graduated cylinder. We'll talk about that later. Thermometer, manometer, anything that forces you to have to think about what the measurement possibly could be, okay? Now, anytime we're reading an analog instrument, you get to have all the numbers that the measuring device has, okay, plus one more, okay? And we'll talk about this, a lot about this in the lab too as we do it. I'm gonna use this thermometer as a good example here. Okay, so we have major markings. These are the ones that have the numbers on them, okay? So this one was broken down by 10 degrees. I'm gonna assume it's Celsius. Don't like having units there. Um, And then in between the major markings, we have minor markings. So all of these guys in between are the minor markings. Okay, these minor markings are 1 degree C because there's 10 of them in the 10-degree gap between the major markings, okay? We get to say those digits when we're measuring something, and we get to add an extra digit to it that's up to us, okay? So if we're gonna read this, I'm gonna draw a line like that. That's a really crappy straight line. Let me draw a little better, maybe. Too much coffee. Yeah, whatever. It's probably right there. Okay. We could say, okay, well, it's more than 100. 1, 2, 3. It's probably 103. Okay. And it's right on the line there, so we can say it's 103.0 degrees Celsius. Okay. This could be Fahrenheit. I don't know. I made it up. All right. Let's try the same thing with this volume of, I'm assuming, water, some clear liquid in this graduated cylinder. All right. So again, here's our major markings where the numbers are. We're gonna assume this is milliliters. So 4 milliliters, 5 milliliters, and then the minor markings are the little guys in between. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minors. So our major markings are every 1 milliliter. Our minor markings are every 0.1 milliliter. So that means our measurement that we read is going to have 2 decimal places to it. Okay, the minor markings give us 1 decimal place, and we can make up another digit that's the second decimal place. So if we read this, it's more than 4 and less than 5. So this is 4.1, 2, 3, 4, 5, but not quite 6. Okay, so 5. And then it's more than 0.5, but less than 0.6. So I'm going to say 4.57. We'll call it milliliters because we have to have a unit on there. There we go. Okay. And we'll get our hands dirty in the lab and measure a whole bunch of stuff so we can get our grasp on how this works. Now, let's think about this idea of accuracy and precision. Okay, these are qualities of the measurement themselves. Okay, accuracy talks about how close your measurement is to the true value of the thing. Okay, unfortunately, you guys as users of stuff, don't really have much control over accuracy. Okay, accuracy depends on, is it high quality equipment? Is it well maintained and all that kind of good stuff? Okay. So is it calibrated correctly? Is it high quality? All that stuff. You can think of it as, and we use bullseyes quite a lot. I'll have some other examples for us too as we do this. That if you're accurate, then you're getting close to the bullseye. Okay, you're getting close to its true value. So that's really what we want to get at. The other side of this is precision. Okay, and precision has to do with how close repeating the same measurement is to itself. How close are repeats of the measurement to each other? Okay, and both of these examples here are precise because all of the measurements or all their shots are all at the same general area. Okay, precision has to do with reproducibility. That's a good word. Okay, so in this case, these people are both very precise because their things are clumped together, but only one of them is being accurate and precise, which is kind of our ideal goal here. Okay. Again, this is more examples. This would be accurate and precise. This is precise but not accurate, and this is neither precise nor accurate. Okay, here's some actual data here as we think through it. I found this graphic when I was looking for stuff, and it really makes, I really liked how it said it. Okay, accuracy is true to the intention, right? How close are you to the real measurement? Precision is how close you are to yourself. So how true to yourself, how true to itself is it? Okay. So obviously our goal when measuring stuff is being accurate and precise as we do it. Okay. I think this is my last slide, but I wanted to talk a little bit about random error versus systematic error. Let me go back to where I have room. Okay. So two main types of error are random versus systematic. Random error is not a big deal. Every measurement has random error. All measure, ugh, I'm sorry about my handwriting. All measurements have random error. Random error is just that, it's random, and if you take enough measurements, this is going to average out. Okay. When you have systematic error, all your data is wrong by the same way. Okay, you're always off by the same amount. Okay, this does not average out. This is likely an instrumentation problem or a user problem. Okay, so if you're reading your instrument wrong, you're going to introduce systematic error, which is going to make your numbers be wrong, and they're always going to be wrong by the same amount because you're always reading it incorrectly. Okay, if we look back here, we can see, okay, this person has random error, okay, because their numbers are kind of all over the place. And so if they took a lot more measurements, they might get closer to the true value of stuff. This person is very precise, but also very wrong. So if this person took a lot more measurements, we could assume that their data would come out to be the same over and over again, and they would always be wrong by the same amount. So this is more systematic error. They're constantly wrong the same way. So taking more measurements and hoping for the best, they're not going to average out. You're going to get the same wrong answer. Okay. If you have any questions or need me for anything, let me know. And I'll see you in another video.